Okay, 2.64 is the final problem in Chapter 2, and it's a callback to the Legendre polynomials from back when we were solving the harmonic oscillator. And basically, this is how we actually get the polynomials themselves. So we have Legendre's differential equation, and in part A, we're going to do a very common method that people use in higher level mathematics to solve very complicated systems, which is that we're going to guess an answer, and we're going to solve for the coefficients to this answer. Because a lot of times in higher math, what you'll find is that there's common patterns in differential equations which will suggest that the answer takes on some form or another. And in this case, if you were actually studying math at this level, you would know that this type of differential solution suggests a power series solution that looks like the form of this. And in part A, we're going to want to obtain a recursive relation for the constants a sub n in this hypothetical power series solution. So we just basically have to plug this back into our differential equation and find the recursive relation. So we have f of x is equal to the summation from n equals 0 to infinity of a n x to the power of n. If we want to derive this with respect to x, we get df by dx is equal to the summation from n equals 0 to infinity. And we just bring out an n, so n times a n times x to the power of n minus 1. And then the second derivative, d2f by dx squared, is going to be done with product rule. This is going to equal the summation from n equals 0 to infinity of n times n minus 1 times a n times x to the power of n minus 1. I'm sorry, not product rule, it's just a derivative, so we just bring it down. Now, at this point, we just plug this back in, and we get that we have the 1 minus x squared times the summation from n equals 0 to infinity of n times n minus 1 times a n times x to the power of n minus 1. And this is subtracted by 2x multiplied by the summation from n equals 0 to infinity of n a n x to the power of n minus 1. And then we're adding l plus 1, and then times the summation n equals 0 to infinity a n x to the power of n, and this is equal to 0. I'm going to use distributive property, and I'm going to expand this a little bit, and this is going to give me a summation from n equals 0 to infinity of n times n minus 1 times a n times x to the n minus 2. And then this is going to be subtracted by the summation from n equals 0 to infinity of n times n minus 1 a n x to the power of n. And then we're going to subtract by the summation of n equals 0 to infinity of 2n a n x to the power of n. We're going to add l times l plus 1, summation n equals 0 to infinity a n x to the power of n is equal to 0. So pretty much all I did here is I just used distributive property and I moved some stuff around to get this new form. Now, at this point, what I'm going to do next is I am going to recognize that, first off, remember, we want a recursive relation for the an terms. So right now, all of these terms are in terms of an. We're going to want some way of defining higher an values given these ans. So immediately, the first thing I see is that I have 4 summations. The one thing that's different here is that this is an x to the power of n minus 2, whereas these are all x to the powers of n. So if I look at this actual summation term, I realize that this is actually equal to 0 for when n is equal to 0 and when n is equal to 1. So there's nothing necessarily stopping me from just upping the index here by 2. So what I mean by that is that the summation from n to 0 to infinity of n times n minus 1 times a n x to the power of n minus 2 is actually exactly the same as saying a summation from n equals 0 to infinity of n plus 2 n plus 1 times a n plus 2 times x to the power of n. So basically all I did was I just added 2 to all these indexes, and I get the same series of terms. It's just I'm excluding the 2 zeros at the very front. So then if I do this, then now if I move everything else to the opposite side, then I get summation n equals 0 to infinity of n plus 2 times n plus 1 times a to the power a sub n plus 2 times x to the power of n is actually equal to the summation from n equals 0 to infinity of n to the power of n minus 1 times a n x to the power of n plus the summation of n equals 0 to infinity 2n a n x to the power of n minus l plus 1 times the summation from n equals 0 to infinity of a n x to the power of n. At this point, I have a common x to the n term everywhere, so I can just get rid of that. My summations are also always the same, so I can get rid of all of those. What I get is n plus 2, n plus 1 times a n plus 2 is equal to n times n minus 1 plus 2n minus l times l plus 1, all multiplied by an. Move it around, and I get now that a n plus 2 is equal to n times n minus 1 plus 2n minus l times l plus 1 divided by n plus 2, n plus 1, and then multiplied by an at the front. And this is my new recursive relation. If I want to clean it up a little bit at the top, I can rewrite this as n squared minus l squared plus n minus l divided by n plus 2, n plus 1, an. And the reason why I'm rewriting it this way is because this is going to make it a little bit easier to see a property that we're going to have to make use of in the later parts. Apologies, I was looking back here and I realized I made a bit of an error, just a very simple error here. When we go from the first derivative to the second derivative over here, the n minus 1 is supposed to change to an n minus 2. That is then, if we carry it over here, this is supposed to be an n minus 2. Thankfully, that didn't get carried over in the error, so that's fine. And then I have a 2x term that gets carried over to x then. So yeah, everything's fine. It's just I did this wrong, but that didn't get carried over, thankfully, so my actual answer is still correct. Okay, in part B, we are told to argue that unless the series truncates, which can only happen if L is an integer, the solution will diverge at x is equal to 1. So let's look at the actual solution form, which is that f of x is in fact equal to the infinite sum from n equals 0 to infinity of a n x to the power of n. So if we make x equal to 1, this is just equal to a summation from n equals 0 to infinity of a sub n. This is an infinite sum. It is going to equal infinity unless this series truncates at some point, which means, a0 is, equal to something, a1 is equal to something, but eventually at some point, an is going to equal 0, and then an plus 1 is going to equal to 0, and it's going to keep on going and equaling 0 forever. That's what truncating means. So this is obviously true. The only way for this to sort of converge is if the an terms eventually start going to 0, so that the sum doesn't keep on going up forever to infinity. Now, this apparently can only happen if L is an integer. So now let's look at the recursive series that we got in part A, which is an plus 2 is equal to n squared minus l squared plus n minus l divided by n plus 1, or n plus 2 times n plus 1, and then an. So you see here that if n is equal to L, then this implies that an plus 2 is going to equal 0, because this top thing is going to equal 0. So because of that, the series will truncate. Alternatively, if n doesn't equal L, then this top term doesn't necessarily equal 0. And remember, n is an integer, so if L is not an integer, then that implies that this series is never going to truncate at any point. Our summation is going to diverge, therefore we don't actually have a valid solution. Now, the other thing to note is that our recursive relation gives us either purely even or purely odd terms for n. If n is even or odd, or sorry, not n, L. If L is even or odd, then we're going to respectively only get even or odd indexes to truncate. The other index doesn't necessarily guarantee to truncate. So because of that, to require it to truncate, we sort of arbitrarily impose the condition that either a0 or a1 is equal to 0, so that sort of the series that doesn't have anything to do with our L term in question, because remember, L is actually what determines our energy, right? So for a given energy, we require that the other set of terms basically just truncates at the base term and equals 0 always. This is an arbitrary requirement. We use it all the time in higher level math when we're dealing with infinite series that have corresponding even and odd terms. In fact, we did this already in an earlier problem in chapter 2 when dealing with the quantum harmonic oscillator. So go back to that chapter and relook at those problems if this is new to you, because it should not be. But yeah, with that, we are done with part B. Okay, so part C, we realized that basically the series for our given solution is basically going to be the Legendre polynomials themselves. So we're asked to find P0, 1, 2, and 3. So let's start with P0. So for P0, L is equal to 0, which is even. So that means all of the odd terms by definition have to equal 0. Therefore, A1 is equal to 0. So that way A3, A5, A7 all equal 0. If we use this recursive relation, right, if n is equal to 0, right, an is equal to, if n is equal to 0 and L is equal to 0, then we have 0 plus 0 at the top. This top thing is 0. That means all successive terms after A0 are 0. Therefore, it truncates at A0. So therefore, A0 is the only non-zero term here. So therefore, P0 of x is just equal to the summation term that we defined earlier, an x to the power of n, which in this case is just A0. So there's your n equals 0 Legendre polynomial. Now let's do P1. So in this case, L is equal to 1. Then we require all the even terms to equal 0. So A0 starts at 0, so that A2, 4, 6 all equal 0. Then we have A1 is just equal to A1. And then A1 plus 2, so n is equal to 1, is then going to equal, according to this term, which I'm going to bring down just for convenience, right? This is 1 plus 2 is going to equal, remember, L is equal to 1, so then 1 minus 1 plus 1 minus 1 over 1 plus 2 times 1 plus 1 times A1. This top both equal 0, so therefore this is equal to 0, so it truncates at A1, therefore P1 of x is just going to equal A1 times x. So there's your P1. Now let's do P2. So L is equal to 2. Therefore, we require the odd terms to just be 0. So A1 is equal to 0. So 3, 5, 7 all equal 0. We have A0 is equal to 0. Then, A0 is equal to A0. So A0 equals itself. Then A0 plus 2. So given n is equal to 0, is equal to 0 minus 2 squared plus 0 minus 2 divided by 0 plus 2 times 0 plus 1. And then multiplied by A0. This is therefore equal to negative 4 minus 2 divided by 2, or negative 3. And then also A0 at the end. So the P2 polynomial is equal to A0 plus A2x squared. And if we plug in A2's term in terms of A0, we get A0 minus 3 A0x squared, just like that. Next, let's do P3, which is the final one. So L is equal to 3, A0 is equal to 0, so all the even terms truncate. We have A1 is equal to itself, and then we have A of 1 plus 2 is equal to, in this case, we have n squared minus L squared, so 1 minus 3 squared times n minus L, plus n minus L, which is going to be 1 minus 3 divided by n plus 2 times n plus 1. So 1 plus 2, 1 plus 1, and then multiplied by A1. So this is going to give us 1 minus 9 plus 1 minus 3 divided by 3 times 2. Is that correct? Minus 9 plus 1 minus 3. Yeah, so that's 2 minus 12, or negative 10 over 6. And let's not forget the A1s. Is equal to negative 5 over 3 times A1. So that means P3 is equal to A1 times x plus a3x cubed, which is equal to a1 times x, minus 5 over third a1x cubed. And that is our answer. And with that, we are done with this problem. We can finally move on to chapter 3.